Hi, I'm going to talk about dot product. That's in section 12.3 of the Stewart textbook. And it's a pretty long section, so I'm splitting it into multiple parts. In this part, I'll talk about what the dot product is and some properties of it. And in the next part, then I'll talk about applications of dot product, including projecting vectors and force and work coming from physics. So those will be in the next part, and this time we'll talk about what the dot product is and what are some of its properties, and some basic applications involving angles. So what's dot product? Well, before we talked about what are vectors, and we talked about some vector operations. The kinds of vector operations we talked about before were vector addition, adding vectors together, and vector subtraction, and scalar multiplication. So multiplying a scalar times a vector, a number times a vector. Well, it turns out that there's other kinds of multiplication rules. There's two more rules for multiplying vectors together, a vector times a vector. And there's two versions of it. There's the dot product, and later we'll talk about the cross product. And these are a couple of different multiplication rules for vectors. So we're going to start with the dot product, and this is a rule for multiplying vectors together, and we'll see what it is. So I'm going to start with just an algebraic formula, and it's kind of a big formula, but we'll dig into it and see how it works and see what it means and come to understand it. But to start with, we're just going to start with this big formula. In Math 275, we're primarily interested in 2 or 3 dimensions, but the dot product is something that works for any number of dimensions, 2, 3, or more. So for right now, we'll just present it for any number of dimensions. But if you want to imagine that this n dimensions was 2, it was just a v1, v2, and nothing else, or this n is 3, so it goes v1, v2, v3, and that's it. Those are familiar situations, but it could be like 5, right? There could be like a v1, v2, v3, v4, v5, or however many. And then same thing for the w. And the only rule for the dot product, there can be as many dimensions as you want, but the v and the w have to have the same number of dimensions. So whatever the number of entries in v, the w is supposed to have the same number of entries as that. And then you get to have a dot product, v dot w. So sometimes people say v dot product w, or sometimes people say v dot w. And then sometimes people use other names like inner product or whatever, but I'm mostly just going to say dot. So v dot w, this is multiplying 2 vectors together, and here's the big formula. V dot w is v1 w1 plus v2 w2, and then you keep going like that. You do v2 w3, v4 w4, v5 w5, and you just go on and until you get to the end. So you take the first entry of v and multiply it with the corresponding first entry of w. And you take the second entry of v and multiply it with the corresponding second entry of w. And you just keep going like that till the end, the last entry of v and the last entry of w. And you add those all up. If you remember your summation notation, this symbol, this is a Greek letter sigma, and it means summation or adding up. And we're adding up vi times wi, where I equals 1, 2, 3, up to n. So this is summation notation. This line is summation notation that means the same thing as the line before. All right, well, that's a kind of crazy formula. You multiply a bunch of stuff and then add a bunch of stuff. We're going to get into what it means and why it's important, but let's just check out a simple example. And here I have 145 dot minus 280. So before anything else, maybe we could ask ourselves, what is the dimension involved here? And what's the n for this example? Do you know? It's 3. It's 3. This is a 3-dimensional example because this vector has 1, 2, 3 entries. All right, so we take the first entry of each one. I have a 1 and a minus 2. And multiply those together. 1 times minus 2. And then we take 4 times 8. The second entry is 4 and 8. And do 4 times 8. And the last entry is 5 and 0. So do 5 times 0. All right, then we're going to add those up. 1 times minus 2 is minus 2. 4 times 8 is 32. And 5 times 0 is 0. So minus 2 plus 32 plus 0, that gives us our 30. So with these vectors, 145 dot minus 280 turned out to be 30. All right, here's a question for you to try. V is 101 and U is 011. Can you compute the dot product? If you want to pause the video and take a moment to think about it. All right, the answer is 1. The answer is 1. So how do we figure that out? V dot U is, well, I multiply the first 2 entries, which are 1 and 0. And then I add that to the second 2 entries that are 0 and 1. And then we add that to the third entries, which are 1 and 1. So I get 0 plus 1. That comes out to be 1. Just out of curiosity, do you know where these wrong answers are coming from? Can you think of a way that a student could make a mistake and come up with these other answers, A, B, and D? I think for the first one, they added the vectors together. This is V plus U. If you added together V plus U, that's what you would get. For V dot U, this is where they multiplied the entries, but forgot to add them up. And made a vector instead. You can see it here, right? When I multiplied the entries, I got 0, 0, 1. And so if you made a vector out of 0, 0, 1, then that's what you would get, 0, 0, 1. That's a thing. That is a thing that people do, but it's not dot product. Dot product is adding them up. And V.U is, well, it's just wrong. I think one way you could get it is they added the entries first and then multiplied. like 1 plus 0 plus 1, adding the v entries, and 0 plus 1 plus 1, adding the u entries, and then multiplying those, you would get 2 times 2. It would be 4. Yeah, don't do that. You gotta multiply them first and then add up those results. Well, okay, so that's computing the dot product. And just a really important observation here, it's on this slide twice, so you know it's important. Dot product is a scalar. The dot product of two vectors is a scalar. So look back at that wrong answer A, right? This student, A and B, both of them, they put vectors as their answer, but you know that can't be right. A dot product is always a scalar output. All right, so we've got our definition of dot product and how to compute a dot product, and we know that the dot product of two vectors is a scalar. We wrote a very algebraic formula for it. So what are some algebraic properties of it? There's a list here of 4 properties. U dot v equals v dot u. And then if I have, in other words, I can switch the order and it gives us the same result. If I multiplied one of the vectors by a scalar, it would be the same thing as doing the original dot product and multiplying the overall result by that number. Or it would be the same thing if I multiplied that number onto the other vector. And then if one of these vectors was broken up as v1 plus v2, then I can multiply each one separately and add the results together. And same thing if it was the u that was broken up as two things added together. We'll see these in action, but right now those are just some equations, and that's not all the properties in the whole world. The textbook actually has some more. Out of curiosity, do you perhaps know the names of these properties? Some of them do have names. You might have heard these names before. The first one, where you can switch the order, that one is called commutative property. It's a commutative property. These last two might remind you of something. Those are both distributive property. It's a distributive. So dot product is distributive over addition, or dot product distributes over vector addition. This second one that I've written, the name is a little bit more obscure. If you go on in mathematics and you study like advanced linear algebra, you'll run into bilinear or multilinear, or it ties in with tensor product. So if you've heard of tensor products, this property is kind of related to that. But it's really not important for us right now, so I'm not going to worry about writing the name down. But commutative and distributive, those are names that maybe you might have heard before in some other class. It's kind of fun to think about why it might be true. So let's just look at the first one for a minute and think about why that might be true. Well, u dot v is u1 v1 plus u2 v2, and you keep going like that till the end. And meanwhile, v dot u is, well, according to the rule, I'm going to take the first entry of the first vector and the first entry of the second vector. Then I take the second entries. I take the second entries of each of them and keep going like that. And now look what's happening here. These terms are the same. because u1 v1 is the same as v1 u1. When I'm looking at this is just multiplying regular numbers. These are not vectors. These are just regular numbers. Multiplying regular numbers is commutative. And now look at the next term. The next term, those are the same, and it's for the same reason. Oh, I chose the wrong purple. Is that a little bit too fussy? Anyway, so in the end, what it comes down to is that dot product of vectors is commutative because multiplying regular numbers is commutative. So commutative property for regular numbers translates directly into commutative property for dot product. So if you want to try this second property and think about why, just do the same thing. Just write out this and sort of write out the terms, and write out this and write out the terms, and you can see why it's true. And same thing for the distributive properties. Just sort of write out what this translates into and write out what that translates into, and it all works out. It's kind of a fun exercise. If you did a trigonometry class with trig identities, it's kind of like that, proving identities. I mean, you don't have to do it. I'm not requiring it, but it's a fun little mini puzzle if you enjoy those things. All right, so those are some algebraic properties of dot product. Like I said, there's some others, but those are some good ones. And as we go forward, we'll soon see how those come into play. And we started with an algebraic definition of dot product, and here's some algebraic properties. So that's not too surprising that algebraic properties would come from an algebraic definition. But what else is there besides algebraic properties? Well, what about geometric properties? There isn't really a super strict definition of algebra versus geometry, but for me, roughly speaking, basically what I think of is anything that looks at the components of vectors is algebraic, and what we've been doing is like super algebraic, right? Because we're like directly multiplying and adding up the components, versus geometric things where you don't directly look at the components. Instead, you look at the direction and magnitude. I haven't even mentioned direction and magnitude up to this point, so that's how you know that it hasn't been geometric. Okay, but can we make it geometric? Can we connect this dot product with geometric things? Yes we can. So let's look at how dot product connects up with magnitude first and then angles. So there's a pretty cool connection between dot product and magnitude. I'm going to illustrate it with an example. I'm going to take a vector 1, 4, 5. It's just some random vector. It's not anything particular. And I'm going to dot it with itself. And look what happens. You take the first entry of each vector, 1, 1, and multiply it. 1 times 1, that's 1 squared. I take the second entry, 4, 4, and multiply them, 4 squared. I take the third entry, 5, 5, 5 and 5, multiply them, 5 squared, and add those up to make the dot product. 1 squared plus 4 squared plus 5 squared. Where have we seen that? Where have we seen a thing where we square the components and add them up? And if you think about it, the magnitude does that, right? The magnitude of 145 would be square the components add them up, and square root that. But since we're squaring the magnitude, that would get rid of the square root. All right, so now you can imagine if there was a different numbers instead of 1, 4, 5, if it was like 3 or whatever, right? 3 times 3 would be 3 squared. It would still tie in with the magnitude. And that's the rule in general for any vector v. When you dot it with itself, v dot v, you always get the magnitude squared. Or in other words, if you take the square root of both sides, the magnitude of v is the square root of v dot v. All right, that's the connection between dot product and magnitude. What about angles? Dot products and angles. All right, let's suppose that we had two vectors v and u, and I would like to know all about u dot v. Except in this imaginary situation, unfortunately, I don't know the components of u and v. Instead of components of u and v, what I know is I know the magnitudes of u and v, and I know the directions of u and v. Remember these EU and EV? Those are symbols that stand for the unit vectors that point in the direction of u and v. So it's like the EU is telling us which direction to look in, and the magnitude is telling us how far to go in that direction. So if we point our vector in that direction and go whatever distance, then that point where we land, that's the end point of the vector, instead of doing components. So it's just another way to describe a vector. And this is what I'm calling quote unquote geometric description. So can we use this quote unquote geometric description to figure out dot products? Well, u dot v, one of our properties was that if I have a scalar multiple of a vector, I can pull that scalar multiple in front. So I'm writing that u dot v, u is magnitude of u times a unit vector, dot product with magnitude of v times a unit vector. And now these scalars, I can pull them in front. Pull scalars in front, and I would end up with the u, magnitude of u in front, magnitude of v in front, and then what's left behind is just the unit vectors. The EU was left inside, and the EV was left inside, but that's all. And that's what's written in this formula. So it just comes from that property where we can pull the scalars in front. Okay, well, I can, if I know the magnitude of u, then I can multiply by that. So I know I can handle that part. If I can multiply by magnitude of v, if I know the magnitude of v, then I can multiply it by it. I know I can handle that part. What about this? That's a unit vector, that's a unit vector. What is the dot product of two unit vectors? Well, let's just say we're in R2 just to make it easier to draw pictures, and we'll figure out a rule that's actually going to work in general, but we're just going to draw pictures for R2. And on top of that, let's say not only are we in R2, but let's say that our first unit vector EU is specifically 1, 0. And then EV is another unit vector. It's got to be somewhere on this unit circle, right? With an angle theta. And if you remember, a point on the unit circle with angle theta means cosine theta comma sine theta. All right, we've made it so specific that now we're able to figure it out. This dot product is, take the first entry 1 times cosine theta, and the second entry 0 times sine theta, add those together. I'm getting cosine theta plus 0. 1 cosine theta plus 0 sine theta gives us cosine theta. Aha. All right, so this is the general rule that we're discovering. In general, the dot product of any two vectors, unit vectors, is the cosine of the angle between them. And I know I worked this out in kind of a specific case. It was in R2, and I sort of assumed one of them was 1, 0. But it's actually a true statement for any two unit vectors, even without those assumptions. So justifying that, why it works more generally, I'm going to kind of skip over the details, but if you're curious, you can think about in terms of a little bit of linear algebra and some rotations if you've covered stuff like that. And if not, you can ask me about it, but I think that's all I'm going to say right now. So the upshot of this statement, we figured out what happens for unit vectors, but the really interesting conclusion is what happens for any vectors. If u and v are any vectors, then look at this business that we got up here. We figured out u dot v is magnitude of u times magnitude of v times the dot product of the unit vectors, and we just figured out the dot product of the unit vectors. It's cosine theta. All right, so u dot v is magnitude of u times magnitude of v times cosine theta. That's a pretty important formula. This is a good one to memorize. We're going to use this a lot as throughout the whole course. This is going to come up constantly. All right, so here's one application of this formula. If you wanted to find theta, you could solve for theta in this equation, right? If you wanted to solve for theta in this equation, you would divide by the magnitude, so it'd have u dot v divided by the magnitudes, and then move the cosine to the other side by doing an inverse cosine, or arc cosine, if you prefer, right? Now we usually choose thetas that are between 0 and pi, like in here. So for example, what do you think is the arc cosine of root 2 over 2? Do you know? If you remember your unit circle, the arc cosine of root 2 over 2 is pi over 4. Or 45 degrees if you're thinking degrees, right? So this angle of pi over 4 has cosine root 2 over 2. It would give you the same cosine if you did minus pi over 4 as your angle. It would have the same horizontal x-coordinate. But we usually choose the pi over 4 instead of minus pi over 4. That's just a choice. Okay, so this is how you can use dot product to find angles between vectors. We saw before how you could use dot product to talk about the magnitude of a vector. The magnitude of a vector you get by dotting the vector with itself and then taking square root. So we got magnitudes, and now here we got angles. All right. Let's try an example. Two straight roads meet at an intersection. the road running south to north gains 20 meters in elevation for every 100 horizontal meters traveled. It has a slope of 1/5. That's a 20% grade. That's steep. The other, running from west to east, loses 10 meters in elevation for every 100 horizontal meters traveled. So downgrade of 10%. What's the angle between these roads? All right, let's see if we can figure this out. So the south-north road, its vector would be going 0, 1. That would be pointing straight north, right in the y direction, but it's sloping up at 1/5. And then the west to east road, that's going along the x-axis, right? That's the horizontal axis. So that should be going 1, 0, but then it has a slope down of -1/10. 10 meters for every 100. So it's just the rise over run. The rise is -10 for every run of 100. All right, so these are the vectors that we want to find the angle between. Let's call them u and v. Okay, now u dot v is 0 plus 0 minus 1/50. So in other words, minus 1/50. And magnitude of u is the square root of 0 squared plus 1 squared plus 1/5 squared. So square root of 1 plus 1/25. And we can simplify it a little bit, 26/25, or square root 26 over 5. Magnitude of v is square root of 1 squared plus 0 squared plus 1/10 squared. So square root of 1 plus 1 100th, or square root of 101 over 10, square root of 101 over 100. So I can make that square root of 101 over 10. And now the dot product divided by the magnitudes would be, that dot product is minus 1/50. And the magnitudes were square root 26 over 5 and square root 101 over 10. And those were multiplied. So it's a little bit of an ugly fraction, I guess, but I think we can simplify it a little bit anyway. So it's -1. So what can you think of to simplify here? If you think about it, we could multiply the top by 50 and we can multiply the bottom by 5 and 10, which is also 50, right? And we'll just get -1 over square root 26 times square root 101. As the top and bottom both have 50ths in them. Okay, so now the upshot is that the angle theta would be the arc cosine of this quantity, -1 over square root 26 times square root 101. Well, to tell you the truth, that's really not a good way to write fractions, because it's not super clear if that 101 is supposed to be under the fraction bar. So let me write that a little better. Okay, well, there's all kinds of things we could do to simplify that. We could actually multiply these square roots together we could actually type it into a calculator and get the decimal, but I leave that to you. You get the idea. Right now, I'm just going to leave it as an exact answer. Well, apparently on this slide, I chose to, I forgot that I did this. Let's compare here. What is this vector? This vector 0, 120 is 100 times our vector u, right? 0 times 100, 1 times 100, a fifth times 100. And then this vector is 100 times vector v. So this is 100u, and this is 100v. And then we worked through and got the same kind of arc cosine thing by doing dot products just like here, but without showing steps. And well, that's the answer you get in radians and degrees. So these roads are a little bit wider than perpendicular. It's a little bit more than a right angle. That makes sense, right? Like one of these roads is going north-south, and one of these like to the north, and one of these roads is going west to east, and that would be 90 degrees. But then you sort of warp them by raising this one up and pushing that one down. So it would be a little wider, a little more than 90 degrees. So that answer of more than 90 degrees kind of fits with the setup. It makes sense. A challenge problem, if you enjoy things like that, if you take opposite points on a circle, so they're across from each other, and R is any other point on the circle, show that the vector from R to P and the vector from R to Q are this. Do you know what that is? That's a perpendicular symbol. And that's actually the next thing we're going to talk about. And these slides are a little bit out of order. This challenge problem should have been after the perpendicular stuff, but I put the slides out of order. Sorry. All right, let's talk about perpendicularness, and then after we talked about it, if you want to try a challenge problem, you could try this. You could try this. Perpendicular right angle. Is that a right angle? Okay, so let's talk about perpendicular and orthogonal. Two vectors are called perpendicular or orthogonal, and the notation is that symbol like that. If and only if u dot v is, okay, do you know the answer? 0. If and only if u dot v is 0. These words, perpendicular and orthogonal, they are synonyms. They're synonymous. They have the same meaning. There's really no difference. They're interchangeable. If you hear me flip-flop between using one or the other, I'm not making a distinction. They really mean the same thing. There's no subtle difference here that I'm ignoring. And they mean a right angle between U and V. The angle between them is acute if the acute means an angle that's less than pi over 2, 90 degrees, and theta being less than pi over 2, if you think about your unit circle, acute angles are on this part of the unit circle. And so the cosine is greater than 0 because it points this way. Obtuse angles are the ones where the angle is greater than pi over 2. So on your unit circle, it's past 90 degrees. It's in this part of the unit circle. So your angle is pointing this way, and that means that the x-coordinate, the horizontal coordinate, is pointing to the left, and those are into the negative numbers. So acute angles are positive cosine, and obtuse angles are negative cosine. And yeah, and the point that I'm supposed to be making is that the cosine being greater than 0 means that the dot product is greater than 0. Because u dot v is just magnitude of u times magnitude of v times cosine theta. And you know that this part is greater than 0, or, well, I guess it could be equal to 0 if one of them was a 0 vector. So the cosine is the only part that could be greater than 0, equals 0, or less than 0. Whatever it is, positive, 0, or negative, in any case, it's getting multiplied by a number that's greater or equal 0. So the overall result will be greater than 0, equals 0, or less than 0. Same as the cosine. So that's why the cosine being greater than 0 corresponds to the dot product being 0. And I guess I can draw a picture like this for right angles. If you want them to be perpendicular or orthogonal, that's what happens here. So that means that the cosine is 0. Cosine of theta is 0. And looking at our equation down here, if the cosine was 0, then the overall multiplication would be whatever times 0. You'd get a 0 result. All right. So do you want to try one? Which of these following vectors is not perpendicular to vector v given by 2i minus 7j? And your choices are u equals 7i plus 2j. Is that perpendicular to v? Or u equals minus 2i plus 7j. Is that perpendicular to v? Or u equals 14i plus 4j plus k? Or u equals 0? I don't know why it doesn't say u equals. You could say u equals 0. Which of them is not perpendicular? Well, let's try it. Let's figure out some dot products. In this case, u dot v is, well, you take the first components, which means the i's, and you multiply them, 7 times 2. And then you take the second components, which is 2 times minus 7. So I'm getting 14 minus 14, that's 0. They are perpendicular. Let's take these, u dot v. Take the first component, that's minus 2 times 2. And take the second component, so I'm getting 7 times minus 7. So I'm getting minus 4 minus 49. That's minus 53. Those are not perpendicular. So there's our answer. This one is not perpendicular. Just for practice sake, we can try it with C and D. Just for practice sake. We don't really need to, but just to demo it, we could do u dot v. So I'm going to take the first components, which are 14i and 2i. So I'm getting 14 times 2. And then the second components, which is the j components, I'm getting 4 times minus 7. And, well, let's see. I've got a 1k here, and I didn't really write k for v, but let's just stick in like a 0k. 0k. Then I'm getting 1 times 0. So I'm getting 28 minus 28. That's 0. So these vectors are perpendicular. And over here, 0 vector means 0i plus 0j. Or I guess 0i plus 0j plus 0k. Either way, u dot v is just 0 times 2 plus 0 times minus 7, getting 0. And those are perpendicular. A little bit weird to think about, like, if I write two vectors like this and I say they're perpendicular with a 90-degree angle, that's okay. If one of them is 0 and the other one is a vector, then I would say those are perpendicular. It's kind of weird, but 0 is perpendicular to every vector. If you think that's weird, 0 is perpendicular to every vector, including itself. That's weird. But that's how it is. Thank you, slides, for telling us the answer. We already know. Do you want to try another question? Can you find a number a to make these vectors orthogonal? The first vector is a comma minus 2, and the second vector is 0, 3. Can you find a number a that makes them to be orthogonal? Just a yes or no question. Well, to solve this, I would want to solve for a in an equation. And our equation is that if we want them to be orthogonal, I need this dot product to be 0. So I want a comma minus 2 dot 0, 3 to be 0. Does that help? Do you want to try solving that equation? You can pause the video and try. So if you try to solve that, you get a times 0 plus minus 2 times 3 equals 0. So just 0 minus 6 equals 0. Or minus 6 equals 0. Well, that equation is not so good. That does not work. Which is just another way of saying that there's no solutions. There's no value of a that makes this work. So, what does that mean in terms of our original question? That means no, we cannot find a number a that makes these orthogonal. And there you have it. Okay, I hope that the translation into an equation made sense here. All right, that's it for dot products. Next, we'll look at the other way to multiply vectors, which is cross products,